Hello students, so I am Dr. Tanmay Vishwash. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we will discuss a very important topic, that is Baeyer-Villiger oxidation. It's an M reaction. This is nothing but oxidation of ketone in presence of peroxide into ester. So today's discussion we will cover a few points like the basic concept, role of each reagent, reaction mechanism, selectivity, nature of peroxide, and some examples. So a lot of chemistry to be learned. Let's start. Before going to details, I have a small request. If you really like my teaching, please motivate me by helping my channel to its growth. Okay. So let's start. As you can see, this Baeyer-Villiger oxidation is nothing but an oxygen transfer reaction from a carbonyl, from a peracid to a carbonyl. So what is peracid? What is the interesting point of this? This is peracid. Let's draw it. This is the peracid. Why? Because this contains this part which is the peroxy linkage. Okay. Generally, how can you prepare? You can prepare, one of the example is acid chloride plus you can take hydrogen peroxide and in presence of alkali. So what could be produced? This will generate react with hydrogen peroxide and produce HOO minus anion, and that will attack here. A question may come that why it will attack not this, because this is more nucleophilic. Okay. So at the end it will result this O minus. For example, if you take sodium, this is the sodium salt, upon acidification you will get the peracid, okay, or better peroxyacid. So this is the interesting point, is that this contains this hydrogen peroxide linkage. So what is interesting? See, this has a lone pair. So there is a repulsion named as alpha effect. What do I mean? This lone pair repulsion, which makes this system a nucleophilic one. Okay. Now question, if you check, it has a canonical form. How? This lone pair could be delocalized here. So what is the canonical form? This is this. So okay, better I am not discussing about this after deprotonation. So the canonical form is this one. So what we can learn from this canonical study? That the availability of this lone pair for any nucleophilic attack is less. So we can say that this lone pair is less nucleophilic. But this, it is not delocalized. So we can expect that this is more nucleophilic. So this is more nucleophilic. So the nucleophilic reaction will happen on this. So first point. So reaction will happen on this oxygen. First point, keep it in mind. Reaction will occur. Point number one. Point number two. See, this is an unstable molecule. So what it want? This molecule want to get this stable conformer. Means this one. So this is a normal acid. So peracid to normal acid. Okay. Another thing, how this could be obtained? By breaking this bond. Okay. And another thing, generally when we say peroxo linkage, means this linkage, and it is say that this peroxo linkage is weak and electron deficient. This statement you listen many times. Question why? First of all, why weak? Although it's a homo, means same atom bond, but because of this lone pair repulsion, this is weak. Point number one. And why electron deficient? See, both are electronegative atom. So this way oxygen is, so that's why this is electron deficient. So it could easily be broken. Please keep it in mind that this could easily be broken, and that is the main reason for their reactivity. Okay. So I guess you have understood or you got some basic understanding about this paracid. So, and if I say in short, what is the nature of this paracid? This nature of this paracid, they are very reactive. Okay, so it's a very reactive molecule and it wants to be stabilized by the removal of 1 unit oxygen, first of all. Second, what type of paracid could be possible? Different type. This is better to write in this way, then you can remember properly. This is MCPBA, highly used. MCPBA, metachloroparbenzoic acid. So even you can use simple parbenzoic acid. This is parbenzoic acid. You can use peroxyacid. This. You can use its trifluoro derivative. This. Now see, if you compare these versus this, difference is this CF3, electron withdrawing. Means this carbon is more electron deficient. So this lone pair devolation is better. I will come, this property is used. So these are different types of paracid and generally their reaction is done in DCM or chloroform like solvent. Generally, I told the word generally their reaction is carried out in such solvent. What do they mean? Generally we observe that hydrogen peroxide mediated oxidations are generally happens in organic medium. Aqueous based medium. So why this is needed? Because hydrogen peroxide is not soluble. It's not an aqueous based medium. And generally what hydrogen peroxide we use 30% solution. 30% means what is the 70%? 70% is water. So when we can't use aqua based reagent, it is highly desirable that we use means in the organic solvent if you want to use, it is better to use these paracids because this DCM or chloroform we can use them. Now actually what reaction is happening? This oxygen, I will prove by mechanism, is transferred here. So this oxygen is actually this. So this is nothing but oxygen transfer reaction, and oxygen addition or elimination is called oxidation reduction. So this is actually a redox reaction. Keep these fact names in your mind because your examiner during the viva could be asked what type of reaction. This is a redox reaction, and when we say redox reaction, some part is oxidized, some one is reduced. So this ketone is oxidized, so this is getting oxidized. So what is reduced? This is reduced. How? See, if you consider the oxidation number of this central carbon, let's consider these are the two carbons, so this is plus 2. Okay, this is plus 3. Okay, and reduction, this oxygen. This oxygen means if you consider this is -1, this is -1. Peroxo linkage. Right now this is -2, this is also -2. So this is the reduction. So this is the overall reaction for this process. And means this description indicates the redox nature of this process. Now, an interesting point that we have understood. Now question, how this reaction is happening. So this is an acid, so in equilibrium it can generate the corresponding acid O minus plus H plus. I agree that this equilibrium is means this its acidity is lesser compared to its corresponding, let's consider this equilibrium. Why? Plus H plus. Why? Because this negative charge is resonance stabilized in this way. So it has this canonical form, this. sorry, this is resonance stabilized, but this charge is not resonance stabilized. Keep it in mind. These lone pair could be delocalized because it is adjacent, but they have a severe repulsion, and that is the main reason for their reactivity. So what happens? We understood that how this is how this peracid ionizes is corresponding to its corresponding acid. So when there is some acid, there is a chance that this acid could be proton at this carbonyl group. So this is H plus. So OH. Now formal charge is here, and it could have a canonical form, that is RCOOH. Positive charge is on carbon. Fine. Now what message is given? Previously this center was electrophilic. Right now, after protonation, it becomes more electrophilic. So if it is more electrophilic, and this is a better nucleophile. Why? Because of alpha effect. So because of alpha effect. You have read this thing. Hydroxylamine, hydrazine, hydrogen peroxide, they are a better nucleophile because of alpha effect. So what happens? That this center attacks. It attacks and it opens. So what is the consequence? Consequence is this is R, this is OH, this is another R, this is O, this R1. In next step, what can happen? There are actually two chances. Two chances means see, what is expected that this bond will break. This oxygen bond will break. Fine. And it will be converted into acid. So what has happened? That it will break. And since this group, this carbonyl is present, means the carboxylic acid, the negative charge on this will be stabilized. Means one product will be RCOO minus. This is a stable anion. Fine. Now questions, this part, much part we have understood. Now since I can see this R migrating, so there are two chances possible, rather say. What? You may consider that one, oxygen. This oxygen can go and attack here, then it can leave. So what will be the product? So product A means path A, if we consider, generally it doesn't happen. I'm trying to give you the justification. So what is expected product? R, C, this is R, O. After attack, this proton will leave this. So this is also another peroxo group, peroxo linkage with a 3-member ring. So it's not stable. So this is not stable. You may think that, sir, why? Because epoxide formation type of reaction we have already studied. So why not this thing can happen? Because of this not stable peroxo oxygen linkage. Previously this is unstable because of peroxo, but this lone pair have some stability with the conjugation of this, but this is not. But another path B, is that it will push and this R group will migrate. So path B. So what will be the product? So B, path B. So this will not happen. Okay. So path B, B is R COOH plus OR. See, this is an ester. So this will remove the proton and this proton will go to itself. So what will be the final product? So after removal of proton, it became ester and it became corresponding acid. So this anion part, let's remove it. So now you can understand how this reaction is happening. So let's draw the transition state. for your better understanding, let's draw the transition state. So in transition state, let me draw it here. Yes, transition state. So what bonds are broken in these? So let's write which bonds are completely intact. So this O H, this bond is broken R. So this bond is fine. So another bond is forming with this R, with this oxygen. This bond is getting broken. This is fine. This is R. Okay, and so this yes, this bond is fine. This is a double bond, another formation. Fine. So this is the TS, transition state. We should denote by this sign. Now question, this what type of migration is this? So this migration is on electrophilic, better to say migration on electron deficient atom. Deficient atom. So generally we preference for the migration on that group which can hold the charge better. First. And there are some migratory aptitude, but I don't want to, I can say in this case some exception happens, because generally we have seen this phenyl group aromatic migrates always better. First hydride, second aromatic, but there are little abnormal thing occur. Here tertiary migrate faster, after that secondary, and that's the thing. So this video I am not encountered that part. I will let you know in a different video, because I believe for HS student this is not essential, it's very complicated, but if you want, if you may visit the next video. So fine, so we have discussed what is the nature of this transition state. Now till now our study was mainly focused on symmetrical substrate. Okay, if R is not equal to R prime, then the migratory aptitude and selectivity issue comes. What I told. Second point, that see, during the reaction, what you have observed, the nature of this leaving means that charge withdrawing also affects a lot. Means the R has a role. What role? If this R is equal to CF3 versus CH3. If it is CF3 for cyclohexanone, so this is the cyclohexanone. So what is the product? Product is this. It is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay, so this is per acid. So this is known as lactone. Please keep this name in your mind. Cyclic esters are called lactone. Lactone or cyclic ester. Okay, so lactone or cyclic ester. So what happened this? And it was observed that this CF3, when this CF3 used as a acid, the reaction rate is faster. What do I mean? If the CF3 reaction rate is 200 times faster. Is it unbelievable? Yes. Why? Because if it is CF3, just imagine, then what is the anion will leave? The anion will leave CF3CO minus. If it is the leaving group, then the negative charge, stabilization of the negative charge means, okay, let me clean it, otherwise it is becoming a little messy. So this negative charge will be delocalized properly. What do I mean? I mean, if it is, it should have a canonical form, that is CF3 COO minus double bond O. So overall, what do I mean? The overall canonical structure is CF3 COO, the minus charge, and because of its minus I effect, it helps to stabilize the negative charge. Okay, and its pK is around, I am not sure, close to 0, means 0.2 like that. So compared to acetic acid, 4.74. Okay, so this is a strong acid. So this is one point. Second point, ultimate product is acid. If the product is acid and along with that another ester, so there is a chance that this ester could be hydrolyzed. What do I mean? That this is a strong acid. For example, let's consider this is a trifluoroparacetic acid. So ultimately trifluoroacetic acid will be a product. So that if R equal to CF3, this is a very strong acid. So what can happen? It can hydrolyze the ester into RCOOH plus ROH plus this R1, means let's consider this part as a CF3. So CF3 COOH. Now it's a very strong acid. So it can do trans-esterification, means this alcohol and this trifluoroacetic acid can result in another ester. What the ester is? CF3COOR. So what we have actually, what we wanted? Actually we wanted this one. Now we are getting along with this one, this is. So this is the unwanted product. This is the unwanted product. Question, we don't want, so how to remove this? Now question, we have to remove this acid. So best way to remove acid is add base like Na2HPO4. This is act as a base and it converts this thing into CF3CO minus Na+. So if when it is a salt, then it will not hamper the reaction. So this is also a condition needed to bring the process forward by abstracting this proton. Okay, so nature of paracid you have also understood. Now a simple question, examples. See, if you take cyclic ester, for example cyclohexanone, will get lactone, and if you take simple ketone, you will get ester. So this is the thing. So I will not prolong this video further. Some unique example I will provide later on, but those will be little difficult examples. So this is the overall discussion about this Baeyer-Villiger oxygen for basic idea. I want to stop it at this basic stage. In next two, I will upload two videos where I will explain first. In first video I will explain, means next video will selectivity, how and why this is. It will be little difficult and complicated. That's why I decided to keep it a separate video. Whoever doesn't want, you may avoid. And another will be with difficult examples. So this is the end of this discussion. So what we have learned today? The basic idea about Baeyer-Villiger oxidation. This oxidation is the conversion of ketone into corresponding ester by the use of paracid, which is acting as a oxidant as well as oxygen transfer reagent. Second, we have discussed the mechanism and why these paracids are so much reactive and what is the consequence. Second, third, the substitution of this R group in paracid, for example CF3CH3, how reactivity pattern changes. And finally, we have discussed the mechanism as well as transition state and few examples. And more interestingly, that in case of cyclic ketone, it produces lactone or cyclic ester. Is another interesting part of this reaction. So thank you everyone. Thanks for your patience to watch this video. If you really like my teaching, please help my channel to grow. First of all, subscribe my channel Chemistry the Mystery of Molecule and please press the bell icon to get the notification of every single video I upload. Secondly, share this video among your friends so that other people who are not aware about this channel or videos, they can also get the benefit from my effort. And most importantly, please like the video and make some good comment, because it proves me that you really enjoy my teaching, and it motivates me also to make new videos for you on a regular basis. So stay happy, stay blessed and stay motivated. See you in my next video.